Just to get at this last thing here. What do you get for this? It should be as though they're all positive, right? All distances considered positive, right? So in other words, you could look at it as the absolute value, right? You could look at the absolute value of the function, right, where everything is above the axis here. So it should be 19.5, right? They're all positive. 3, 12, 4.5. If you just count them all up, you get 19.5. If you do the absolute value of that function, okay, integral of absolute value of that function, if you wanted to do it on a calculator or something like that. Really, analytically, to do integral of absolute value, you just have to split it apart into separate chunks anyways, right? If you wanted to do this, if you had the function for it and actually did it that way, the reason I'm telling you this absolute value thing is if you're working with something on the calculator, you can use that numerical integration of absolute value of the function. That makes all the distances positive, right? Because it puts all the pieces of the graph up above. There's a couple questions here. It seems that relating it to velocity, position, that's the best thing because you're most familiar with it. Although you're most familiar when acceleration is constant. This is not constant, right? Not constant. 2.4 times t, right? So this is not a projectile, like it's not like a projectile where the acceleration is constant. If you integrate this a couple times, the position function here would be what in the end? It would be, this is a first degree function. The velocity is going to be a quadratic. The position function would be a cubic. So it's not going to be something that we're familiar with here. The only problem when you get to here is, note the units. This is in miles per hour. This is 8 seconds, right? So you have to think about that, how you're going to deal with that. This is very weird units here. Acceleration in miles per hour per second. You know how you have, in physics you usually use, if somebody says what are the units on acceleration, it's meters per second squared, right? Of course that actually means meters per second per second. You could write these kind of weird units, and in this situation it makes sense, right? How many miles per hour are you gaining each second, right? If you're accelerating a car, miles per hour per second it's another unit that you can use for acceleration, of course, because it's not miles. I better say miles with a mi, of course. It's a distance per time, even though these are different. If you're going to integrate it the first time, you have to integrate it where you're using seconds. But then if you're going to integrate it a second time to get back to position, you have to work with hours. All right. So if we have that function and we want how fast is the car going when the 8 seconds are up, we want its velocity, right? How fast? Find its velocity. You want its velocity at 8 seconds, right? Its velocity at 8 seconds is going to be whatever its velocity was at 0 plus net change in velocity from 0 to 8. Does that make sense? Let me write it so I have more room here. Take a second to wrap your brain around that. I better write this way because I'm writing the same thing. Net change in velocity from 0 to 8. So you're saying, what was its velocity at a certain time, plus however much it changed from 0 to 8. I think you're given its velocity at 0, aren't you? 5 miles per hour? 5. Plus its net change. If we have something again that's in miles per hour per second, and we integrate it with respect to seconds, that's going to disappear and we're going to get something in miles per hour, right? Just like when you work backwards to find derivatives, if you started something that was in meters and you looked at this was something in seconds, then the slope was in meters per second. And if you found the derivative again with respect to seconds, you got meters per second squared. It works the same going the other way. If you have something that's in meters per second squared and you integrate it with respect to time in seconds, it's going to first get rid of that, and then it's going to get rid of that. You're going to be back to meters, right? Whatever the units are. Now, maybe this is too early to have something where there's weird units like this, miles per hour per second. How do we write the net change in velocity from 0 to 8 using an integral? Integral from 0 to 8 of this, right? Of 2.4 t with respect to t. This is the net change here that's the net change in velocity from 0 to 8. This thing says miles per hour per second, so we can put seconds right here. If it's miles per hour per second, this is okay if these are seconds. Down here, it's not going to be okay. Okay? So let's figure out what that is. What is that? 5 plus. If you want to do it analytically, of course, you got to go an antiderivative of this. 1.2 t squared, right? If you do integral of t is a half t squared. 8, 0. Run out of the room here. I have to put it over here. What does that give you? Five plus 76.8. 81.8. So after 8 seconds, it's going 81.8 miles per hour, right? That's its speed after that. It would be nice if you kind of confirm this with a graph. We should get this one out, I guess. Make it easier. What? Say that again. The units are miles per hour per second. So when you integrate it with respect to time in seconds, you lose this, right? If your units are miles per hour per second, you got to use seconds here, right? You have to integrate it with respect to time in seconds. If this was miles per hour, these would have to be hours. The next one, since we first get rid of this and now we have just miles per hour, here you got to use miles, right? When you're using an integral, you can't go 0 to 8 again, right? If you want how far did the car travel. Should we look at the graph of the part A first? If you put I guess it doesn't matter this one which calculator we use. Okay, that's the acceleration function, 2.4x. If you want this value, if you do the integral from 0 to 8, so we want calc. If we want it to show on the graph here, 0, 8, it's going to shade in that area from 0 to 8. That area is 76.8. We could have written a function for the velocity. Whoops. We could have written a function for the velocity right off the bat that was this, right? We could have actually written the function for velocity and said if we wanted, now this is still part A, I'm going to write it down here though. We could have written a function for velocity is the velocity at 0 plus the indefinite integral of this, right? We have to sub in the number after, basically. What you should do is not put that. You should put some constant in here and sub the value that you have that you know that it's 5 at the beginning, at 0. For what we know, basically we know this is just going to be the initial velocity. If you actually want a function here for this, you can find the indefinite integral, 1.2 t squared, plus some constant, and say that this is 5 at 0 and sub it in and work out that this constant is 5. We can leave that for now. But it is possible. Okay? That net change there in the calculator, area under the curve. If you want this thing now, you can use the same strategy here. How far did the car travel? So in other words, you want its displacement. So you want the integral of what we have here, right? of this thing. You want the area under this velocity curve. So actually, we do need the function for that, don't we? We need to know that velocity is, it started at 5 plus its 1.2 t squared. And again, you can find that if you had called this a constant, and you said that this was 5 over here. Okay, it started at 5 at 0. Starts at 5 plus that. Oh my goodness, I'm at 10.